I'm Norman Wildberger. We've started now the second part of this course in hyperbolic geometry, where we're now concentrating on metrical issues. Last time we talked about Pythagoras' theorem, which is the most important theorem in the subject. Today we're going to talk about the triple quad formula, which is the second most important theorem in the subject. Here's what it says, that if you have three collinear points in hyperbolic geometry, with quadrances Q1, Q2, and Q3 between them, then those three quadrances satisfy this relation. Q1 plus Q2 plus Q3 all squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared plus 4 Q1, Q2, Q3. It's a relation which is of degree 3 because there's a cubic term right there. However, it's quadratic in any one of the variables. This is a very important formula in mathematics. Let's start today by illustrating how this actually works in a concrete example. So here are 3 points which are collinear. The point 2 to 0 to 1, the point 1 to 1 to 2, and the point minus 1 to 1 to 1. Where are these points? Well, when we visualize the points in the plane, like we like to do, because it's relatively simple, a two-dimensional picture, then A1 is the point 2, 0, because the Z being 1 means that we can interpret these two coordinates as being the ordinary X and Y coordinates. So 2, 0, there's A1 right there. How about this point, 1 to 1 to 2? Well, here the Z coordinate is not equal to 1. So if we want to relate this to a point in the XY plane, we should divide all 3 numbers by 2, making that Z coordinate equal to 1, and then the X and the Y coordinates are 1/2, 1/2. So there's how we picture A2. And A3 is minus 1, 1. It's right up there, and you can check that those 3 points are collinear. In fact, they all lie on the line 1 to 3 to 2. Let's check that. That's the equation of this line. Incidence is determined by this times this plus this times this minus this times this equals 0. And it does equal 0. Similarly, 1 times 1 plus 1 times 3 minus 2 times 2 is 0. So this point and this line are also incident. And finally, minus 1 times 1 plus 1 times 3 minus 1 times 2 is also 0. So all these 3 points lie on this line. This is the line with equation x plus 3y equals 2. Another way of checking that the 3 points are collinear is by computing a determinant. If we put the 3 coordinates along the rows of the matrix and take the determinant of that matrix, then we get 0. And let me remind you that the determinant of a 3 by 3 matrix like this is the sum of 3 terms with plus and minus signs. It's 2 times 1 times 1 minus 2 times 2 times 1. And then there's a kind of a corresponding thing when you move everything over to the right. So 0 times, well, this times this minus this times this, but that's all 0 because that's 0. And then plus 1 times 1 minus minus 1, or 2. So altogether we're getting 2 minus 4, that's minus 2, and then plus 2 equals 0. So these 3 points are collinear. Now let's calculate the quadrances between them. They are Q1 equals 3, Q2 equals minus 2, and Q3 equals 1. So this means that the quadrants between A2 and A3 is the number 3. Let's check that using the formula. So what's our formula for the quadrants between these 2 points? It's 1 minus a certain fraction. The numerator of that fraction is 1 times minus 1 plus 1 times 1 minus 2 times 1 all squared. So what is that? It's minus 1 plus 1 minus 2, so that's minus 2 squared, that's 4. So the numerator is 4. The denominator is the product of 1 plus 1 minus 4 with 1 plus 1 minus 1. In other words, 2 minus 4, that's minus 2 times 1. So what did we say? We have 4 over minus 2, giving a total of minus 2. So the quadrant is 1 minus minus 2, which is 3. So I'll let you check also that Q2 is minus 2 and Q3 equals 1. Quadrants being 1 has a special significance. It means that these 2 points, A1 and A2, are in fact perpendicular. And geometrically what that means is that if you take the dual of A1, you get a line that passes through A2. And if you take the dual of A2, you get a line which passes through A1. Okay, now let's verify that the triple quad formula is satisfied. This theorem says that in such a situation, these 3 numbers must satisfy this relation. So let's check that. 3 minus 2 plus 1 all squared is 2 times 3 squared plus minus 2 squared plus 1 squared plus 4 times the product. 3 times minus 2 times 1. Is this true? Well, that's 3 minus 2 plus 1 all squared. That's 4 on the left-hand side. And over here we have 10, 14 times 2. That's 28 minus 24. That's also 4. So the triple quad formula is satisfied. It's good exercise for you to take a couple of points that are collinear, compute quadrances, verify that they satisfy the triple quad formula, so that you get some confidence that this rather remarkable formula does actually work all the time. So we want to understand this triple quad formula. And to do that, it's useful to go back to rational trigonometry in the plane and compare the formula to the corresponding formula there. So let me remind you that I would like you to think in terms of geometry as having 2 sides, the affine side and the projective side. In this course, we're working in the hyperbolic setting, which is really a projective geometry. In the rational trigonometry setting, we're working in the Euclidean framework. This is an affine setting. So let's just have a look at how various things compare between these 2 geometries. Here's the formula for the quadrants between 2 points. Difference in x coordinates squared plus difference in y coordinates squared. Here was the formula for the quadrants in the hyperbolic setting. 1 minus an expression like this, sort of a dot product squared divided by the product of 2 dot products at the bottom. Pythagoras' theorem, Q3 equals Q1 plus Q2, is equivalent to having a right angle between 2 of the sides of the triangle. In other words, this side and this side being perpendicular. And I remind you that in the Euclidean case, the interpretation of that is really as areas of squares. Each of these quadrants is naturally interpreted as the area of the square built on the side of the corresponding triangle. That's how Euclid thought about Pythagoras. In the hyperbolic setting, the Pythagoras' theorem had this form, which was a deformation of this one. Q3 equals Q1 plus Q2 minus Q1 Q2. So it's being deformed a little bit by adding this quadratic term to the end. Now, in rational trigonometry, there's also, of course, a relation between the 3 quadrants formed by 3 collinear points. And here it is here. It's the triple quad formula in the Euclidean setting. Q1 plus Q2 plus Q3 all squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared. So it's really the relation between the areas of 3 squares determined by 3 collinear points. Over here in our hyperbolic setting, the triple quad formula that we're studying today has a very similar kind of form, except that there is again a deformation, an added term, which is a little bit of a higher degree. This cubic term plus 4, Q1, Q2, Q3 distinguishes it from the affine formula. So we see that the projective formulas are a little bit more complicated than the affine formulas, but kind of follow the same path. That might make you think that projective geometry is a more complicated situation, and there's something to be said for that. But it's also true that the hyperbolic setting or the projective setting has some aspects which make it simpler than the affine setting. In particular, the duality that we've talked about between points and lines and between quadrants and spreads is something that we get over here that we don't get over here, which makes life a lot simpler for us in many aspects. Now, another difference to be aware of is that here the implications are both ways. Here, the implications are in one direction only. If the lines are perpendicular, then the formula is satisfied. If the points are collinear, then the formula is satisfied. We don't have the implications going the other way. That's another important difference between the affine setting and the projective setting. Of course, there's another very important connection between the hyperbolic triple quad formula and one of the other formulas of rational trigonometry. And that's the triple spread formula, which concern the three spreads formed by a triangle. The three spreads S1, S2, and S3 of a triangle satisfy the triple spread formula, which is exactly the same as the formula that we're talking about here today about the quadrances formed by three collinear points in the hyperbolic setting. This is obviously more than a coincidence. So there should be some kind of explanation. Why are these two formulas the same? So I'm now going to give you a little bit of an explanation as to why we can expect that to occur. The first thing to observe is that the three spreads of a triangle are the same as the three spreads formed by corresponding concurrent lines. If we take this line here and we translate it so that it's always parallel, then the spreads that it makes with the other two lines don't change. In particular, if we move it all the way so that it's down here, then the spread that it makes with this line is the same spread that this line made with this line. In other words, it's S2. And similarly, this spread S1 here is still the same as this spread S1 here. It means that the triple spread formula in the rational trigonometry setting can also be interpreted as being a relation between the three spreads formed by three concurrent lines. So you have three lines, 1, 2, 3, going through a point. The three spreads formed by them satisfies also the triple spread formula. The next thing we have to understand is that the spread in the rational trigonometry setting can be written like this in terms of a little bit of linear algebra. So let me explain that. If you have two lines, say this line here and this line here, and suppose this line is determined by a vector v1 and this line is determined by a vector v2, then the spread between these two lines can be expressed in terms of the dot product of the vector v1 with v2 and the dot product of v1 with itself and the dot product of v2 with itself. So this is a rewriting of the spread. It's a very nice way of rewriting it because it has a certain generality. It turns out that this spread can be used as a definition for general dot products. What does it mean? Well, it means in linear algebra there's ways of modifying the familiar dot product to give more general ones. And it turns out that in an arbitrary linear space, you can define the spread between two lines using exactly this formula. The quadrants, the associated quadrants, is just also given in terms of the dot product. It's the dot product of a vector with itself. And then a sort of remarkable thing happens. It turns out that the 5 main laws of rational trigonometry that I told you about last time still hold in this more general setting. That's why it's a universal kind of geometry. It's not just working for the Euclidean dot product, it's also working for more general dot products, which are often more technically called symmetric bilinear forms. So without going into precise definitions here, because I just want to give you a general orientation, here is the familiar dot product in the ordinary two-dimensional plane. If you have one vector x1, y1, another vector x2, y2, then the dot product between them is a number. And it's the number x1, x2 plus y1, y2. You can extend that dot product to one in 3 dimensions. So if you have 2 vectors x1, y1, z1 and x2, y2, z2, you can define the dot product between them to be x1, x2 plus y1, y2 plus z1, z2. But there are also other kinds of dot products. For example, relativistic dot products. In 2 dimensions, where you just modify this definition by changing this plus sign to a minus sign. So as I mentioned a little bit in my rational trigonometry series, Wild Trig, this leads to a geometry which I call red geometry. It's a sort of a baby relativistic geometry in 2 dimensions, and if one sort of orients oneself towards studying it from the point of view of the quadrants and spread determined by this dot product, then one gets a very pleasant geometry which shares many of the features of Euclidean geometry, but also is quite different geometrically. So you can look up red geometry in the Wild Trig series if you'd like to know more about that. You can also go to 3 dimensions where you have vectors x1, y1, z1, x2, y2, z2, and you define the dot product between them just like here, but with a minus sign in front of the z1, z2. That's starting to look quite familiar because that's very much like the kinds of objects that occur in our hyperbolic formulation of things. And in fact, there's a very intimate connection between the hyperbolic geometry that we're studying and this relativistic kind of geometry formed from this kind of dot product. So putting these things together, I now want to give you an explanation of why the hyperbolic triple quad formula should be the same as the triple spread formula in rational trigonometry. Okay. So I remind you that a hyperbolic point for us, thing that we've been calling A, has an interpretation as a line through the origin in 3-dimensional space. So 2 points, A1 and A2, can be thought of as 2 different lines going through the origin in 3-dimensional x, y space. And we defined the quadrants between them in terms of an expression exactly like this. 1 minus v1 dot v2 squared divided by v1 dot v1, v2 dot v2, where we were using this as the dot product. So our formula for the quadrants is exactly this kind of thing where we're using this dot product. In other words, it has the interpretation of being a spread between these 2 vectors. In other words, what we're calling a hyperbolic quadrants has another interpretation in affine geometry as a spread between 2 lines. So this is a sort of an explanation of why I like to think of hyperbolic geometry as, in some sense, projective relativistic geometry. The points that we're studying in hyperbolic geometry are just lines in really a hyperbolic affine space. We're looking at 3-dimensional hyperbolic space projectively, in other words, with our eye at the origin, so we can only see things emanating from the origin, be they lines or planes. So why does the triple quad formula hold? Well, suppose we have 3 collinear hyperbolic points, A1, A2, A3. Then geometrically what that means is that we have 3 lines through the origin in this 3-dimensional space. And those 3 lines are collinear. Well, what does that mean? Well, it simply means that they lie in a plane. There's a plane through the origin, represented here by this red sheet. Should think of that as a plane through the origin. And all three lines lie on that red sheet. Now we're generally trying to visualize things in our viewing plane, z equals 1 up here. And such a plane will meet this viewing plane in fact, a line. So to say that the 3 points are collinear, you can either think of it two-dimensionally in terms of these 3 points as lying on that line, or you can think of it three-dimensionally as these 3 lines in the three-dimensional space lying in a plane. Okay, so if you have 3 lines which are in a plane, then the 3 spreads formed by those lines, say S1, S2, S3, are going to satisfy the triple spread formula in the affine three-dimensional space. Now, I haven't proven that, I'm just telling you that that's the way the world works. Okay? That the laws of rational trigonometry extend to higher dimensions and they extend to arbitrary quadratic forms. But if you're willing to believe that, then the point is that what we're calling the triple quad formula between 3 hyperbolic points is really the same as the triple spread formula for these 3 lines in three-dimensional space. And that's why the 2 formulas agree. Now, okay, that's a little bit of a complicated explanation, involves some more advanced concepts. We're going three-dimensional space and quadratic forms and dot products and so on. So don't worry too much if that went over your head. But just I want to give you that as a kind of an explanation you can come back to and think about that some more. So while I'm talking about these slightly more advanced things, let me make this note here. A rather important point. That the 4 main laws of hyperbolic trigonometry, which we're studying now, like Pythagoras' theorem, the triple quad formula, the spread law, and the cross law, they hold, in fact, for more general dot products or symmetric bilinear forms. And in particular, it will turn out that exactly those laws also hold in elliptic, or sometimes called spherical trigonometry. So when we come to studying the sphere and trigonometry on a sphere, we are going to discover that exactly the same laws that we're currently studying apply in this situation without any modification. So exactly the same laws. In the classical point of view, hyperbolic geometry and spherical geometry have formulas which are parallel, but they're quite different. These ones involve sines, these will involve shines. In this point of view, universal geometry, they're all really the same. They're governed by the same laws. It's another strong indication of the essential rightness of this point of view. All right, so we've been looking at this hyperbolic triple quad formula. Now it's time to get to grips, roll up our sleeves, and see if we can prove it. Why is this actually true? So here's the official statement. The triple quad formula. If the points A1, A2, A3 are collinear, and we define these 3 quadrants, Q1 is the quadrants between A2, A3, Q2 the quadrants between A1, A3, and Q3 the quadrants between A1 and A2, then Q1 plus Q2 plus Q3 all squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared plus 4 Q1, Q2, Q3. We're not going to prove this. It comes down to remarkable algebraic identities, which are more remarkable than the ones that we needed for Pythagoras' theorem. So minor miracles intervene to make this work. First, we're going to check that the difference between the left and right hand side here, so this thing minus this thing minus this thing, that whole thing there, can be rewritten in a convenient way. And it's kind of interesting. It's 4 times 1 minus Q1, 1 minus Q2, 1 minus Q3, minus Q1 plus Q2 plus Q3 minus 2, all squared. So this, as an expression involving Q1, Q2, and Q3, is equal to this, as an expression involving Q1, Q2, Q3. This is an algebraic identity that exists independent of any kind of geometry. This difference between the left and right-hand side is important enough to give it a little bit of a name. So let's introduce this triple spread function S. S of Q1, Q2, Q3 is defined to be this thing here. Okay, so now let's suppose that our 3 points have specific coordinates, x1 to y1 to z1, and so on as before. The quadrances, what are they? Well, I'm writing down the quadrances here in slightly different way. I'm writing 1 minus q1, 1 minus q2, and 1 minus q3 because I want to kind of exploit this formula here. So remember that q1 is equal to 1 minus this thing. So we're just writing it in a slightly different way. 1 minus q1 equals this. This is exactly from the definition of q1. And there's the definition of q2, and there's the definition of q3. Now let's consider for a second what would happen if we replaced 1 minus q1, 1 minus q2, and 1 minus q3 with these 3 expressions. We would get something that's a square. That's the important point. That if you take this thing, it's not a square, but if you take it and multiply it with this one and with this one, then you do get a square. Why? Because the numerators, first of all, are all squares. And when you multiply all of these 3 denominators together, you get, say, this x2 squared term twice. Once from here and once from here. And you get the x3 squared terms twice, once from there and once from there, and the x1 squared terms twice, once from here and once from there. Conveniently, 4 is also a square. So this is then a difference of squares. We want to show that this thing is 0. Okay? So the fact that this is a difference of squares is convenient, and that's the same idea that we had in Pythagoras' theorem. To show that it's 0, all we need to do is to show that one of the 2 factors is 0. And a difference of squares can be very easily factored as a squared minus b squared is a minus b times a plus b. This is exactly the same argument we used for the proof of Pythagoras' theorem in the last video. So let's have a look. What does this factor that we need look like? Okay, so there's the S function again. I've just rewritten it again so we can have a look at it. So this is then now a difference of squares. That's a square, that's a square. And so if this is a squared minus b squared, then the 2 factors are a minus b and a plus b. And one of the factors is a minus b. So what happened there is this whole thing became the square of this. So 2 squared is 4. And then I remind you that these things here in the numerators, they all appeared with squares. So we're just removing the squares there. And each of these 3 terms on the bottom occurred twice, and we're now just using it once. So if this is a squared minus b squared, then this is like a. And now we're going to look at minus b. Well, there it is right there, minus b. And I've rewritten the q1 plus q2 plus q3 minus 2 all squared as 1 minus q1 plus 1 minus q2 plus 1 minus q3 minus 1 all squared. So that's actually 2 minus q1 minus q2 minus q3 all squared. And because it's a square, we can multiply by minus 1 inside. It doesn't change things. But if we do it that way, then the b factor is 1 minus q1 plus 1 minus q2 plus 1 minus q3 minus 1. And so a minus b, there's a minus b. Okay, so 1 minus q1, there it is right there. 1 minus q2, there it is right there. 1 minus q3, there it is there. And, well, the minus 1, the minus sign, plus 1 at the end. So one of these factors is this thing minus this, minus this, minus this, plus 1. That's all one big expression. How are we going to simplify that? We're going to get it over a common denominator. We almost have common denominators. Here's the obvious candidate for the common denominator. So we're going to have to multiply this thing here by x1 squared and so on. We're going to have to multiply this one by x2 squared and so on, this one by x3 squared and so on, and this one by all three together. So in the numerator, we're going to get 2 times this product minus this times x1 squared and so on, minus this times x2 squared and so on, minus this times x3 squared and so on, plus this times this times this. Now remarkably, it's an identity that that numerator up to a minus sign turns out exactly to be this thing all squared. It's absolutely remarkable. It's like a miracle. It's a fabulous identity. It's a big identity, okay? Obviously, I use my computer to find this. But it's not impossible to do it by hand. If you have a couple of hours, you can write this all down, big piece of paper, very carefully, work it all out. You can check that when you expand it all out, you get the same thing as this thing here. Finding it is maybe not so easy, but you can check that it's true once you know that you have it in front of you. Now, the nice thing about this is that the numerator here is exactly this determinant. Well, there's a square, so it's this determinant squared. And this is the determinant formed by the three components of A1, A2, and A3. And we know that is 0 if A1, A2, and A3 are collinear. So the argument is, if A1, A2, and A3 are collinear, then this numerator is 0, so this expression is 0. So this expression is 0. So one of the factors of this is 0, and so this is 0. And that's the triple quad formula. And that's the proof. It's not easy. It's one of the main theorems of mathematics. So it shouldn't be entirely easy. It has real content. Okay, it is a powerful result. Let me observe, just as we did for Pythagoras' theorem, that the converse does not obviously hold, for exactly the same reason. If we know that this expression is 0, then we can conclude that one of the two factors is 0. But it might not be this one. It might be the other factor which we haven't written down. So we cannot immediately conclude that this determinant is 0 from knowing that this S of Q1, Q2, Q3 is 0. Now, many students of mathematics these days are weak in algebra. They have not spent enough time and effort learning and working with algebraic expressions. Chances are you might be in that boat. You may have studied mathematics at university, you may have ticked the boxes and you passed those various courses, but ultimately your algebra is weak, and that's going to prevent you from really learning mathematics well. Okay, so if you're a student of the modern educational system, there's a very good chance that your algebra is weak, and this kind of exercise, analyzing this, working it all out, is excellent practice to strengthen your algebraic skills. It's like weightlifting for mathematics. All right, so there's nothing better that I can imagine you do on a rainy afternoon than get there with a big piece of paper and say, I'm going to check this all out. I'm going to expand some of these things out. I'm going to make sure that what he's saying here really does work. Get some sense for manipulating these polynomials around. It's all polynomial identities ultimately. And let me just say, it doesn't necessarily mean that you have to write everything out. Right? You could be a little bit intelligent because there's a lot of symmetry in these expressions. So once you figured out that there's a kind of an expression like this, then you can kind of see that the pattern continues and you get other expressions too. So you can use a little bit of intelligence in understanding the patterns and applying symmetry to make life easier. Okay, it's the second most important theorem in hyperbolic geometry. It's one of the key theorems in mathematics. It has ramifications in many directions, as we will see as we go along. Let's give you now some exercises. We'll give you some more appreciation for this wonderful formula, the triple quad formula, and this function S. Let's give this function a name. Let's say that S of A, B, C, this thing here, is the triple spread function. And our first exercise is to give a few alternate forms for it. Expand it out to check that you get that. Check that in fact we can rewrite it like this, which we've already used in the proof. And here it is as a determinant with a minus sign of a rather pleasant symmetric 4x4 matrix. Show that the triple quad formula in the second exercise can be rewritten as this thing here as a quadratic equation. So instead of a symmetric equation between Q1, Q2, and Q3, we can rewrite it if, say, we wanted to solve for Q3 in terms of Q1 and Q2. It's actually quite a useful formula. For the third exercise, verify that the triple spread function can be rewritten this way, as 1 minus c times this minus a plus b minus 1 squared. That might seem rather curious, but it's very useful to deduce an important result, what we'll call the complementary quadrances theorem, which says that if you have three collinear points, A1, A2, and A3, and one of the quadrances is 1, then the sum of the other two quadrances is 1. So if one of the quadrances is 1, it means two of the points are perpendicular, then the other two quadrances add up to 1. The fourth exercise, verify that you can also rewrite the triple spread function in this way as a minus b times something minus c times c minus 4a plus 4a squared. And deduce from that the equal quadrances theorem, very important theorem, that if A1, A2, A3 are collinear points and you happen to know that Q1 equals Q2, then the third quadrant is either 0 or 4 times Q1 times 1 minus Q1. It's a very important expression in hyperbolic trigonometry, actually also in rational trigonometry. It actually turns out to be the second spread polynomial. We'll talk about that later on. But this is a very important result, so you get to check it from an algebraic identity involving this triple spread function. Okay, so you've done well following all of this. It's a pretty hefty algebra, isn't it? But we're accomplishing very important things here. Before we move on to the next trigonometric laws, I want to give you a little bit of light relief, and we're going to look at some more pictures. I want you to get a better familiarity with what quadrants means intuitively, pictorially. So we're going to do that by looking at circles next time. This will give us a good solidification of our understanding of quadrants. You'll get more expert in being able to understand what the quadrants means geometrically. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.